Welcome to today's statistics tutorial. Today we're going to be looking at the Central Limit Theorem, the Central Limit Theorem for sample means, and the Central Limit Theorem for sums. We'll be going through all of their formulas, explain the differences between the three sets of formulas, and also show you how to calculate for probabilities, percentiles, and any type of questions that you might encounter in your homework in regards to Central Limit Theorem.
So with Central Limit Theorem, so basically what the Central Limit Theorem is saying is that if you have a distribution, and it could be any type of distribution, and you pulled a sample of numbers, repeatedly pull a sample from that distribution and took their mean, then all of those means together are going to form a normal distribution, regardless of what the shape of the original distribution looks like. And preferably, you want a sample size greater than or equal to 30. And the sampling has always been with replacement. So every single trial has the same condition. So that's basically what it means with words. So now let's look at just kind of an example so we can make some sense of what they're talking about. So let's just take, and this is a small sample, but just to kind of get an idea of what they're talking about. If I said that I had a sample space of 1, 1, 1, 1, 3, 4, 4, 6, 6, 6. So that would be a sample space with 10 items. Then that frequency distribution would look like this. So if I have 1, 2, 3, 4, 5, 6. So I'm going to just do a dot plot of the frequency distribution for this particular sample space. So I've got 3 6s, I've got 2 4s, 1 3, and I've got 4 1s. Okay, so we can see just from this distribution, this does not look like a normal distribution. And then if I was to take the mean of this particular space, so that would be taking the mean, which is just summing up all of those numbers and dividing them by the number of samples, then that's going to give me 33. So all I'm doing is adding all of these digits together, dividing them by 10, because I have 10 numbers. Then I get that average. That gives me 3.3. So that tells me that my mu, or mean, right here is about 3.3. So what the Central Limit Theorem is going to say is that if I take a sample of this distribution and take their mean, then it's going to have my average, the mean, it's going to have the same mean, and over time, if I take a whole bunch of samples, it's going to form the shape of a normal curve. And that's actually not very good. Try that again. So if I take a whole bunch of the means and then I plot them, then over time, it's going to have a normal distribution. So that's basically what it's saying. So let's look at some trials. So let's say from here, I did a random sample size of n equals 4 from this sample space. So my first one, when I just randomly chose some numbers, I got the sample space of 3, 4, 1, and 6. And then I'm going to take the mean of that space, of that one, and that gave me 3.5. So then I'm going to go ahead and I'm going to plot that out and see what it looks like. If I had 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, we'll go to there. So the first one gives me a dot at 3.5. So I'm also going to do, so this is a frequency distribution. And I'm going to do another frequency distribution here, just to kind of see what these are going to plot out. So then I'm going to take another one. And I'm just randomly drawing from this set. And draw a 6, a 1, a 1, and a 1. Then I'm going to take the average of that space, and that's going to give me a 2.25. 0.25. Okay? So, and then I went and I did this 20 times. So let's just start looking. I'm not going to write down all of these numbers, but I'm going to go ahead and show you what the plot is. And so you can see how it's going to start to build, and it's going to start to look like this normal distribution. So my first one, I got a 3.5. The second time, I got a 2.25. My next one, I got a 4. Then I got a 1.75. Then I got a 3. Then I got a 2.5. Then I got a 2.75. I got another 3. I got another 3.5. I got a 2.25. Then I got a 3.5, another 3.5, 1.75, 4.25, a 2, a 3.5, a 2.25, another 3.5, another 3.5, a 2.5, and a 4.75. Okay? So as you can see, I've done 20 trials, but you were starting to see that this is starting to take the shape of a bell curve. And so this would be an n equals 4. And this is called a sampling distribution of the sample mean. And if you watch the first video in your in that chapter, the Caz Academy has an example that's similar to this, and they've also got a digital demonstration of how they took the samples, and then as you continue over time, then the more and more pieces of data you've got, it's going to form the shape of a normal distribution. Okay, any questions so far? So this is basically what they're talking about, just so that you have a visual. And what it's saying is that as this sample, so right now we have 10 numbers, I've got a sample size of 4, so as this sample size increases, then we're going to get more and more, this is going to look like a normal distribution. Okay, So now let's look at what the formulas are and how do we use this with a problem. So the central theorem, so the central limit theorem for the sample mean, the central limit theorem for the sample mean has the following formulas. So the notation is going to be this x average, or the mean, n for your normal distribution, and then it's going to be mu of x, comma, sigma x divided by the square root of n. Okay, so your mu of x is going to be the same mean as your original distribution. Those stay the same. Your standard deviation, or your sigma x, is going to be equal to the original standard deviation squared, the square root of the original standard deviation squared divided by n, where n is the number in your sample size. And you can either write it as square root with the square, or you can also, and you'll see it more often, with the sigma over the square root of n. And I find it's helpful if you can remember both of these formulas, because sometimes the math is easier if you're n, you can square root it, then write it like this. If you can't, if this is a number that's going to give you like a weird decimal or weird, it's not going to be a clean number, then oftentimes the math is a little easier if you take your sigma and square it, divide it by n, and then take your square root of the whole thing together. And then your n is your sample size. So for example, in the problem that we did here, up above, so let's just say, I didn't give it a standard deviation, but let's say I had n equals 4, because that was my sample size. My mu is going to be the same, so that was 3.3. So that's going to be the same for both of them. And then let's say I start with a standard deviation. And just for fun, so you can see how this works, let's say I have a standard deviation of 3. Then my standard deviation for the sample mean would be 3 squared divided by 4. And I can write that as 3 over square root of 4, which is the same as 3/2, which is 1.5. Okay, so my standard deviation for the sample mean would be 1.5, the mean would be 3.3, and my n would be 4. So then if I wanted to find a probability, then I would just use the normal distribution probabilities online calculator. So let's just say I wanted to find the probability that my x is going to be between, let's say, 2.5 and 3.5. So then I'm going to come over here to my calculator, click on normal distribution. I'm going to put in my mean. I'm going to put in my standard deviation. So my mean is 3.3. My mean is standard deviation 1.5. Then I'm going to click on my probability, put in those numbers. And then I'm going to hit my calculate button. It's going to give me the answer. So it's a 0.256. So just a little over a quarter of percent probability that it's, and it's then also going to graph it. Okay, any questions? Okay. Let's go ahead and I'm going to give you a new whiteboard, and let's do another problem. Okay, so let's do it again. Oh, the other formula that you need to know is your z-score. So let's write the formulas again. This is for the sample means, your notation. Oops. Okay, so you've got X. You've got the normal distribution, your mu of X, sigma over the square root of n. So this is the notation. Your mu of X is going to be the same as the original. Your standard deviation is going to be the square root of the original divided by the number of the sample size. This is also known as the standard, so it's called the standard deviation of the mean. It's also called the standard error of the mean. And then the other formula you might need is your z-score, which just tells you the number of standard deviations away from the mean. And it's the exact same formula that you saw in the normal distribution. So it's your x value minus the mean divided by your standard deviation. And then if it wants to ask for, wants you to solve for an x value, then you're just going to rewrite that equation as your z-score. So that's your z of x times your standard deviation of x plus the mean of x. So once again, your z-score, so your mean, your z-score equations, those are exactly the same as what you did with the normal distribution, same formula. Okay? So those are your main equations. Let's do another example. Let's say we're given an unknown distribution where the mean equals, I'm going to do this in a different color to separate it from the formulas. So let's say you're given a mean of 90, a standard deviation is 15, a sample size of n equals 25, and which is drawn randomly from the population. So the first thing we want to do is we want to find the probability that the sample mean is between 85 and 92. So that means we're going to find the probability that this X value is going to be between 85 and 92. So the first thing we need to do is I need to plug in these formulas. So my mean of X is going to be the same as the mean, so that's going to be 90. My standard deviation is going to be the square root of my standard deviation, my standard deviation squared divided by n. So that's going to be the square root of 15 squared divided by 25. And I can rewrite that as 15 divided by the square root of 25. And that's just going to be 15 divided by 5, which is going to give me 3. So 3 is my standard deviation of the mean. So now I've got the mean and the standard deviation and a probability that I want to solve. So now the next thing I'm going to do is I'm going to go to my normal distribution calculator. I'm going to put in the mean of 90. Standard deviation is going to be 3. I want to find the probability that it's between 85 and 92. I'm going to put in my calculate, and it's going to give me an answer of 0.699717. So I can approximate that as about 0.70. So about 70% probability. Okay, any questions? Okay, so now the next thing, it says find the value that is 2 standard deviations above the expected value 90 of the sample mean. Okay, so for that, we're wanting to find the value. So in your book, it's going to be written like this. The value equals the mean plus the number of standard deviations times your sigma, which is just the original sigma, over square root of n. So that's the formula that they're going to give you. But if you remember, this is just the same as what we put up here, finding your x value using your z-score. So this is your mean of the mean of the mean, the mean of the sample, plus your z-score of the sample. So if you'll recall, this found a number of standard deviations. We saw this in Module 2, and then this was redefined as a z-score in Module 6. And then your sigma over n squared is just your standard deviation of the mean. Okay, so then to solve this, we're going to plug in the numbers. To solve for x, we're going to plug in our mean. Our mean is 90. Plus, they tell us we want to find 2 standard deviations above the expected. So that tells us our z-score, we're going to be given a z-score of 2. And then we're going to get our standard deviation, and that's a 3. So 2 times 3 equals 6. plus 90 is going to give me 96. So 96 is the value that is 2 standard deviations above the mean. Any questions about how I solved for that? Okay, let's do another one. So let's do this one in green because we're doing another example. So let's say we have the mean is 45. The original standard deviation is 8. We're going to draw a sample size of 30. And I want to find the probability that the mean value or the x value is going to be between 42 and 50. Then I'm going to, once again, my mean of the sample is going to be the same as the mean of the original, which will be 45. My mean of the sample is going to be the square root of the original standard deviation squared divided by the sample size. So that's going to give me the square root of 8 squared all over 30. Now, if you notice, the square root of 30 is not going to be a clean number. So this would be an example of when you'd want to take the square, divide it, and then take the square root. So this is going to be 64 divided by 30, which is going to be the square root of 2.13, which gives me 1.46. Then I'm going to go to my online calculator, put in the mean, it's 45. The standard deviation is 1.46. And then I want to find the probability, 42, that x is between 42 and 50. Hit my calculate button, and it's going to give me an answer of 0.9797. Okay, so that means I've got about a 98% probability that x is going to fall within that range. Okay, any questions? Okay, let's do one more example, and then we'll find a probability, and then we'll also find the percentile for a sample mean. So this one, let's say we're given the mean is 34, the standard deviation is 15. We're going to take a sample size of 100. And we want to find the probability that x is going to be greater than 30. So once again, we're going to take the mean. We want to get the mean of the sample. It's going to be the same as the mean of the original, so that's 34. The standard deviation of the sample is the square root of the original standard deviation squared divided by n. So that's going to give me a standard deviation of 1.5. So then I'm going to go here and back to my online calculator, plug in the mean of 34, standard deviation 1.5, and this time we're solving for x is greater than 30. So So I can get rid of these numbers here, put in my calculate, and it's going to give me an answer of 0.99617. So this is almost 100%. So I'm just going to put it as 99.6% probability that X is going to be greater than 30. So it's almost 100% that X is going to be greater than 30. So now let's say they want to find the 99th percentile, the 95th percentile for the sample mean. The 5th percentile. So with that, that just means we want to find the probability that the X value is going to be less than K, equals 0.95. So we're solving for a number. So this is K is at the 95th percentile. So now we're going to have the same mean, the same standard deviation, but this time we're going to use the inverse probability on our online calculator. And where these question marks are, that's the same as where the K would be. And then we're going to just type in our 0.95 for the 95th percentile. Hit calculate. It's going to give me my value for K. So this number in red is my K value. So that gives me K equals 36.46, which I'm going to just round up at 36.5. So we can see that it's about right here. So where that ends, or the starting point on your graph, that is your K value. And everything shaded is your 90, so that shaded area would be your 95th percentile, saying that all of those values are within the 95%, are below, are 95% below that K value of 36.5. And then everything above it, the white area, would be everything that is 5% greater. Okay, any questions? Okay, and you can unmute yourself or just enter questions in the chat box if you have any questions. Okay, so let's move on to the central limit theorem for sums. So this was the central limit theorem for means. Now we're going to do the central limit theorem for sums. Let me give you a new whiteboard. And you can save these whiteboards if you click on the link. If you save on the whiteboard, then you'll have access to all of this material for 3 weeks. Okay, so now we want the central limit theorem for sums. And the formula, so what this means is that if you take the samples, all of the samples, and you sum those values together, sum their means together, you're going to have another normal distribution. It's going to form its own normal distribution. And the only thing that's going to be different is the mean and the standard deviations are going to be different values, but it's still going to have that normal distribution curve it's going to form, which is called the sampling distribution. So the notation for the central limit theorem for sums is the summation of x, n for the normal distribution, and your mean is n, which is the sample size, times the mean of the sample. So the sample size times the original mean gives you the mean of the sum. And then for your standard deviation, it's going to be the square root of the sample times the original standard deviation. So let's kind of write these formulas out a little bit. So the mean for the sum is going to be n, which is the size, times, so this is the formula, and this is the sample size times the original mean of, or the mean of the original distribution. So one thing that you want to be careful with the notation is that they use the same mean to the x with a subscript of x. Use that same symbol for the sums that they do with the means, but this mean is referring to the original mean of from the original distribution. So this is your sample size times the original mean. Then your standard deviation, okay, your standard deviation for the sum is going to be the square root of n, which is the sample size, times the original standard deviation. So it's the square root of the sample times the original standard deviation. And then your z-score, or the number of standard deviations, is going to equal the summation of x, your sums of your x, minus your mean, which is your n, times the original mean, all divided by the standard deviation, which is the square root of n, times the original standard deviation. So if you'll notice, this formula is exactly the same formula as what you used for the normal distribution z-scores, or when in Module 6, when we had covered normal distributions, it's exactly the same formula. It's x minus the mean divided by the standard deviation. And then once again, if I want to move that around to solve for the x value using those z-scores, then you would say your x value is going to equal your z-score times the square root of the sample size times the original standard deviation plus the sample size times the original mean. Any questions about any of those formulas? Okay, so those are the formulas you're going to need to know for the central limit theorem for sums. So let's go ahead and do some examples. So let's say you're given a problem where you have the mean is 90, standard deviation is 15, and the sample size is 80. Is 80. And we want to find the probability that x, the sum of x's, is going to be greater than 7,500. So the sum of x equals the sum of the 80 values. My mu, the mean, okay, so then I'm going to have my notation is going to be the summation of x, normal distribution, the 80, because I have my formulas, n times the mean, so it's going to be 80 times the 90 is going to be my mean, and my standard deviation is going to be the square root of 80 times 15. So let's write that out. The mean of the sums is going to be 80 times 90, which is going to be 7,200. The standard deviation of the sums is going to be the square root of 80 times 15, which is going to give me 134.16. And the sum of the values, sum of the 80 values, is going to be, so we have x, we want to know if it's going to be greater than 7,500. So then I'm going to come back here to my online calculator. I'm going to put in a mean of 7,200. Standard deviation is going to be 134.16. Then I'm going to find the probability that x is greater than 7,500. Go ahead and take this one off and hit calculate, which gives me an answer of 0.012671. So that's pretty close to, that's about a 1% or 1.3% probability that x is going to be greater than 7,500. And we can see that on the graph, that that's just a very small amount showing on the graph. Okay, any questions so far? Okay, so now let's say that it asks for find the sum that is 1.5 standard deviations above the mean of the sum. So now they're giving us a z-score of 1.5, and we want to find that x value. So we're going to plug that into our formula of e to the x equals our mean, which is the 7,200, plus the z-score times our standard deviation, which is our 134.16. Oh, you're welcome. I'm glad it's helpful. And then when you multiply, you're going to multiply these two together, add it to the mean, and that is going to give you a value of 7401.24. So this is your x value, where z is 1.5 standard deviations above the mean. Okay. Okay, let's do another one, another problem with solving for the sums, and then we'll do a problem where they ask you for both, to solve for both the mean and the sum. So let's do another one. So with a lot of these, it's just basically with the central limit theorem, if you know your formulas and have a general understanding of what the formulas are supposed to be doing, then it's just a matter of plugging numbers into the formulas, then you plug it into the online calculator. And unfortunately, I think your book was really vague and kind of confusing on how they explained this chapter, because it's actually a very simple concept, but it kind of sounded confusing once you started adding the formulas with the way your book was presenting it. So let's do another problem. We've got the mean is 35, standard deviation is 10. We want to have a sample size of 39. So let's say we want to find the probability that the sum of x is going to be between 1,400 and 1,500. So then I need to do my conversions again. So my mean of the sum of x, and I'm just writing slightly different notation. You can just write mean, but this is really what it is. It's the mean of the sum of x is equal to n times the mean of x. So that's going to be 39 times 35, which is going to give you 1365. And then my standard deviation of the sum of x is going to be the square root of the sample size times the original standard deviation. So that's going to give me 39 times 10. Excuse me, the square root of 39 times 10, which is going to give me 62.45. Once again, I'm going to go ahead and just put those in my online calculator. The mean is going to be 1365. Standard deviation, oops, I left some numbers out. That should be 62.45. Then we're going to find the probability. The probability that the sum of x's is between 1,400 and 1,500. And I'm going to just do my calculations. And that's going to give me about a 27% probability. Now let's say they want to find k, we want to find the 90th percentile. Then we're going to keep the same values. We're just going to look for the inverse probability. So we're going to take that probability. The sum of x is going to be less than k and set that equal to 0.90. So now I'm going to just plug that in over here on the inverse probability. Go ahead and clear these guys. And then once again, that number in red is going to be my k value. So my k is going to equal about 145. And this k value is right here where the graph changes. So the shaded part is the 90th percentile, and then everything above it would, so it would say, the shaded part says everything below that is 90% below the k value, and everything above it in the unshaded would be 10% above the k value. Okay, any questions? Okay, let's do one more problem. So I'm going to get a new board, and then this time the problem is going to be just a little bit different. Okay, so I'm going to actually pull a picture. So give me a second while I grab a picture with the problem. Okay, so this one has, let me see here. So we're going to look at this problem. This problem, there we go. So a study involving stress was conducted among students on a college campus. The stress scores follow a uniform distribution with the lowest stress score equal to 1 and the highest equal to 5. Using a sample of 75 students, find 1, the probability that the mean stress score for the 75 students is less than 2, the 90th percentile for the mean stress score for the 75 students. 3 is the probability that the total of the 75 stress scores is less than 200. And 4, the 90th percentile for the total stress scores for the 75 students. And let x equal 1 stress score. So you want to recognize that these first two problems, I didn't do that very well. Okay, so this first two are doing the central limit theorem for the means. And the second two problems are asking questions for the central limit theorem for the sum. And this also says that this is using a uniform distribution with the lowest scores equal to 1, highest equal to 5. Okay, so in all of our previous problems, they've given us just an unknown distribution, and they've given us the original mean and standard deviation. So this time they are they're telling you that the distribution is a uniform distribution. So the first thing you're going to need to do is find what is your original mean and standard deviation. So if you recall from Module 5, uniform distribution, our formula is going to be x u UAB, and our mean is going to be A plus B over 2, and our standard deviation is going to be the square root of the square of B minus A squared divided by 12. So, and they're giving us that A equals 1, because that's our lowest score, and our highest score is a 5. So remember, if we're going to look at what does this look like, just as a refresher from Module 5, our A score, so if this is 0, that's going to be 1, this is going to be 5, and this is going to be 1 over 4 because it's 5 minus 1. So that's what this is what our original distribution is going to look like. So now, let's plug in those numbers to get our mean and our standard deviation. So our mean is going to be 1 plus 5 over 2. So that's going to be 6 over 2, which is going to equal 3. And our standard deviation is going to be the square root of 5 minus 1 squared divided by 12. So that's the square root of 4 squared, which is 16 over 12. So that's going to be the square root of 1.33, which is going to give me a 1.15. Okay, so that gives me my original standard deviation is 1.15. The original mean is 3. So now we're going to just plug in our formulas. So for problem number 1, I'm going to use our central limit theorem for the mean. So let's do that in green here. So I'm going to have my central limit, so my x's, and so remember, so this is going to be your mean, and it's going to be the standard deviation square root n. So my n is going to be 75. My mean of x is going to be the same as the original mean, so that's going to be 3. My standard deviation is going to be the original standard deviation divided by the square root of n. So that's going to be 1.15 divided by the square root of 75. And since the square root of 75 isn't an easy number, then I'm going to go back to where I have the square of 115, and make that 1.33 over 75, which gives me the square root of 0.0177 equals 0.133 as my standard deviation. Okay, any questions about what I just did here, why I changed this? Okay, so this, just to kind of review, so this is the square sigma divided by the square root of n. And remember that you can also make that sigma squared divided by n and then square root. So sometimes you need to kind of reverse it a little bit in order to make the math simpler. So going back to here, we can plug that in and just say this is x, and our mean is going to be 3. Our sigma is going to be 0.133 for our notation. Okay, so now we have all of the numbers we need in order to solve our problem. Okay, so the first one says we want to know what is the probability that the mean score for the 75 students is going to be less than 2. So this is problem number 1. So we're going to go back to our digital camera, or online, not camera, our online calculator, and we're going to plug in a mean of 3. Standard deviation is 0.133. We want to find the probability that x is going to be less than 2. Take that one off, hit in the calculator, and it tells us 0. We can see it's not going to show up on the graph. And this makes sense because it says the smallest stress score is going to be equal to 1. So we wouldn't expect that any of the means or the averages to be that much smaller. And as you can see, it looks like somewhere between probably about 2.5 is when it kind of disappears on your graph. So we wouldn't expect any of those values to be that low. Okay, problem number 2 wants us to find the 90th percentile for the mean stress score for the 75 students. So we're going to do the same thing, but this time we're solving for K. So we're going to come back here to the inverse. We're going to solve for K at the 90th percentile using the same mean and standard deviation. Click in the calculate. The number in red is K. So that tells me that K is going to equal about 3.17. And we can see that that's about right here where the shaded and white areas change. Okay, any questions? Okay, let's go on to the second half of this problem. The second half of the problem is wanting to use the total of the 75 stress scores. So that tells us we're going to use the Central Limit Theorem for sum. So that notation is we're going to let the sum of x is going to equal the sum of the 75 scores. The notation is the summation of x, the normal distribution, and then plugging in the numbers for that. Well, I'll write down the formula first. So this is n times mu and the square root of n times sigma. So that's going to be the summation of x, the normal distribution. N is 75 times the mean, which is going to be the same, the original mean, which is our 3. And then our standard deviation is going to be the square root of 75 times the original standard deviation, which is 1.15. And we'll go ahead and solve these. So the mean of the sum is going to be the size of the sample times the original mean, which is going to give me 225. And then the standard deviation for the sum is going to equal the square root of the sample size times the original standard deviation. So that's going to give me 9.959. So we'll just say 9.96. Go ahead and put these in the calculator. So our mean is going to be 225. Standard deviation is going to be 9.96. And then we want to know, so for our for question number 3, we want the probability that the summation of x is going to be less than 200. So we're going to go probability x less than 200. Go ahead and clear that. Hit calculate. And once again, this is also pretty small value. That's going to be 0.006036. So we have about a 0.6% probability that it's going to be less than 200. The fourth problem, the last problem, okay, so, and then the last problem is finding the 90th percentile. So we want to find the 90th percentile. So we're going to take the probability, the summation of x is going to be less than k is equal to 0.90. So we're going to use the same values. And once again, we're going to put this in as 0.90. Clear the other probability, and the number in red is going to be your k value, which is going to give me k equals 237.764. So I'm going to just round that up to 237.8. Once again, that's right here where the graph changes from the shaded to the non-shaded. Any questions about anything that we've gone over?
Everything makes sense.
Good.
See the links below for additional supports and resources, as well as the normal distribution calculator. Be sure to like and subscribe to get the latest videos by Caz Academy. Thanks for watching, and I'll see you at the next video.